Right. Hello, everyone. So I'd like to welcome everyone, live audience, as well as the virtual participants. We are broadcasting here from Glasgow. This is a global monitoring project for Global Stocktake 2023. We are happy to have everyone here. Thank you for coming. So this event is hosted by the Ministry of Environment Japan, MOEJ, and co-hosted by Japan Aerospace Exploration Agency, JAXA, and the National Institute for Environment Studies, NIES. So I'm Tomohiro Oda. I'm a senior scientist at University Space Research Association, non-profit research organization located in the Greater Washington area. I started my science career in Japan. And since then, I have been working on greenhouse gas emission, and now in the US. I'm honored to serve as your moderator for today. During the event, we'd like to take your questions. And if you're joining online, please submit your question via chat box or email. Later part of this event, we're trying to answer this question. So now, from Ministry of Environment, host of this event, we have Mr. Ryuzo Sugimoto, the Director of the International Cooperation and the Sustainable Infrastructure Office at MOEJ. 杉本さん、お願いします。
Thank you very much. Good afternoon, everyone. I'm Ryuzo Sugimoto, the Director of the International Cooperation Office, Cooperation and Sustainable Infrastructure Office at the Ministry of Environment, Japan. Thank you very much for coming today to this Japan Pavilion side event, GHG monitoring project for the global stocktake. I'd like to say a few introductory words on behalf of the Ministry of the Environment. Under the Paris Agreement, the parties agreed on setting their climate action plans to achieve rapid greenhouse gas emissions reduction and mitigation goals, known as NDCs, and collectively reviewing nations' progress every 5 years for defining more ambitious plans. This new reviewing process is called the global stocktake. It is a key for the success of the Paris Agreement and where Japan will contribute and play a leading role through the scientific and technological innovations. This seminar event is an ideal opportunity to showcase our ongoing research activities that directly respond to the needs for the global stocktake. Our speakers today will present a variety of the research activities to support the global stocktakes based on our best scientists. We invite speakers not only from research institutions in Japan, but also from our wonderful international colleagues, Dr. David Crisp from the Jet Propulsion Laboratory in the US, who will show us about the international coordination of the space-based GHG measurement activities and his expectations from Japan. Now, the first speaker, Dr. Akihiko Ito, from the National Institute for Environmental Studies, or NIES, will share the detail of our project in his talk titled Comprehensive Study on Large-Scale Monitoring and Modeling of GHG Budgets. The Ministry of the Environment Japan started the research project this past April. This project aimed to establish a prototype system to support monitoring and reporting of GHG emissions from both human and natural resources at multiple scales. The prototype system is expected to be delivered by 2023. That is the year of the first global stocktake. The system employs various observations and quantitative the system employs various observations and modeling techniques and will support our transparency, consistency, and quantitatively and timely assessment of the GHG emissions. In particular, the project is fully utilizing observational data collected from the wide variety of the observations platform we have, such as ground-based stations, aircraft, ships, and satellite, and conducting advanced modeling studies. Dr. Ito is going to walk you through how Japan will contribute to the Global Stocktake 2023 based on our ongoing researches. In conclusion, I hope that this seminar will be an opportunity to encourage decarbonization effort and lead new partnerships. Thank you very much for your kind attention. Thank you.
Thank you, Sugimoto-san. So now we invite Dr. Ito. So Dr. Akihiko Ito is the head of the biogeochemical modeling and analysis section at NIS. He's an expert of ecological modeling. He has been studying the impacts of ecological processes on the climate change. So Ito-san, the floor is yours.
Thank you, Oda-san. It's my great pleasure to be here at the World Leading Climate Summit. And I'm very happy to present our new project. Called S2 project, S28 project, funded by the Ministry of Environment. Next, please. As you know, the Global Stocktake is a 5-year periodical event to make the national NDC, nationally determined contribution, to be more ambitious. So we need best available science to achieve this 5-year cycle. So the first Global Stocktake will take place in 2023, but the process now started. The data and information collection phase now started. So we researchers should provide the best available scientific data to this it's a very important processes. Next, please. So the Ministry of Environment of Japan started a 3-year project from this April. So this project is called S28, Comprehensive Study on Multi-Scale Monitoring and Modeling of Greenhouse Gases. So this project consists of 3 themes. Theme 1 focuses on the observation of atmospheric greenhouse gas dynamics and atmospheric inversion models called MICAM. And theme 3 conduct a bottom-up study of the greenhouse gas budget using inventory and biochemical models. And also, the theme 2 is very, very important to conduct a future projection of climate change to examine the effectiveness of emission reductions. So through the mutual validation, we provide the best available scientific data to the Global Stocktake. This is our basic concept of the S28 project. Next, please. This is an overview of our observation in Asia. Asia is the very sparse region in the global observation, but we have a very fruitful, plenty of research equipment in this area by the ground-based observation and aircraft measurement, ship measurement, and so on. So we will combine this as research facilities into one system, a comprehensive system, to provide a very good data. The right-hand side uses an example of the atmospheric measurement of Tokyo Skytree area and comparison with the aircraft measurement and emission inventory developed by Oda-san Odiak, and uses the example of Kumira, a South Asian site for the methane and methane isotope dynamics in this area, and uses the the tracer component of the Chinese methane and carbon dioxide emissions. Using this data, we can detect the impact of COVID-19 in this case, and we have a near real-time data set. And finally, we can provide this data to the general public for the transparency of our approach. Next, please. And using this data, we can simulate the very high-resolution global greenhouse gas transport using a transport model called NICAM, developed by Niwa-san in our institute. So using this model has a high resolution as high as 14 kilometers and simulates the dynamics of atmospheric CO2 and methane dynamics. We can simulate the methane concentration as you see bottom here. And by using this model in inversion mode, we can estimate the land surface or ocean surface budget of greenhouse gases. As you see right-hand side, we can compare the seasonal change of the model simulation and atmospheric observation. And this high-resolution model allows us the comparison between the specific site simulation result and observation site result. This is an example of the Tokyo Skytree result. This is very impressive result. Next, please. We also conduct bottom-up simulations. This is an example of the bottom-up greenhouse gas budget estimation for the CO2, methane, and nitrous oxide using the anthropogenic emission inventory EDGAR version 6 and the biogeochemical simulation result by Digit model and biomass burning emission by GFED product. This approach, bottom-up approach, has advantage in spatial resolution and sector resolution. But this approach is susceptible to the various kinds of uncertainties. So we need verification by comparing with other independent data of ground data or top-down simulation data. Next, please. So finally, what can we provide for the global stocktake? This S28 project can provide a top-down estimation of greenhouse gas estimation budget at the land surface and atmospheric observation data. And the bottom-up estimation can also provide the data of land surface greenhouse gas budget, CO2, methane, and N2O at the global and regional scales. So this data will be available through database to the general public for the transparency, and we will publicate the annual report of greenhouse gas budget including this data. So through this our best available scientific product, we want to make the contribution to the global stocktake in the future. That's all. Thank you very much.
Thank you, Ito-san. So now we're ready to introduce next speaker, which is the Dr. Hiroshi Shito from JAXA. Dr. Shito is an associate and senior engineer at JAXA. He is an expert of remote sensing instrument from space. He has been working on GOSAT satellite, also now GOSAT 2. He'll be telling us what he's seeing from the observation from space and what the implication to the global stocktake. Shito-san, take it away.
Can you hear me?
Yes, perfectly.
Okay, thank you, Oda-san. So I'm Hiroshi Shito from JAXA. So I'm very happy to present our recent greenhouse gas observation activity by using the satellite. In our JAXA, we operating the GOSAT and the GOSAT 2 to detecting the global CO2 and methane And now, regarding the GOSAT satellite, it's operating over the decade. So today, I'd like to present the decade-long global greenhouse gas observation by greenhouse gas observing satellite. GOSAT towards the global stocktake. Okay. So our GOSAT is Japan's first greenhouse gas dedicated satellite and was launched in January 2009. So GOSAT can measure both solar reflected light on Earth's surface in SWIR bands and thermal emissions in TIR bands to observe CO2 and methane. Also, GOSAT has the unique access of two-axis agile pointing system, which allow us to provide two observation modes. One is the grid mode. So the left panel is illustrated the grid observation image from the space, and the other one is the target mode. It's also illustrated in the right panel in the bottom. So, as you well know, the cities are responsible for the more than 70% of the global total greenhouse gas emission. Then, we have to consider how to estimate the global anthropogenic emission accurately. To respond to this question, we have been continuously performed the intense target observation over world megacity to capture the emissions. Since 2009, GOSAT continuously observed the global CO2 and methane every 3 days and frequently targeting the large city over 50 locations more than 12.5 years. As you can see in this figure, GOSAT data clearly present that the global and the local density, CO2 density is increasing year by year with seasonal variation from 2009 to 2020. Utilizing both solar reflected light and thermal emissions observed by GOSAT, JAXA Earth Observation Research Center has newly developed the algorithm to derive the partial carbon information for emission studies. We assume that the upper partial carbon result represents background CO2 concentration, which are less affected by the city, while the lower panel carbon results track the CO2 concentration changes within the city or near surface. The boundary layer of the partial column is defined as illustration, so we define using the retrieved surface pressure. Applying this new algorithm, we reprocess the entire GOSAT observation data. This figure presents the seasonal CO2 and methane changes at different latitude bands over land from 2009 to 2021. So as you can see, the amplitudes of lower troposphere result is much higher than that of the conventional total carbon result. In other words, these data are highly sensitive for the emissions related with our human activities. So if you have an interest in our new data set, please contact us. We also try to derive the CO2 change over Tokyo and Beijing for January through April. of each year from 2016 to 2020, the monthly average CO2 enhancement over Tokyo and Beijing in the bar graph in the black panel, and the target map from the GOSAT observation are illustrated in the left figures. All months in 2020 show reduced CO2 enhancement relative to prior years. While this behavior is consistent with the reported COVID-19 related reduction of fossil fuel emissions. In addition to this, the megacity CO2 enhancement estimated using the partial common density retrieve are overall consistent with ODIAC inventory. We are trying to retrieve the emission rate over the megacity like New York City, New Delhi, Riyadh, Beijing, Shanghai. So this calculation is based on our new product. So JAXA will release the state-of-the-art partial carbon product in public as a contribution to global community for improving their understanding of the carbon cycle towards the global stocktakes. So thank you very much for your attention.
Thank you so much, To-san. So for the live audience, if you have a question, we will try to address them at the earlier part of the panel discussion. So a little bit. Also, if you're calling in virtually, you're welcome to submit a question to the chat box as you do. So our next speaker will be Dr. Prabir Patra. Dr. Patra serves as a principal scientist at the Earth Systems Analysis Center at JAMSTEC, Yokohama. He's an expert of the global inverse modeling of greenhouse gas, such as carbon dioxide, methane, also nitrogen oxide. He'll be telling us his inverse modeling analysis, also the implication to the global stocktake. Patra-san, what was yours?
Thank you very much, Oda-san. So I think after this wonderful introduction, I don't need to read my first page. And just to also tell you that I am part of the project which Ito-san presented, and then one of the items we deliver through that the new project, that the process of CO2 and methane N2O. And with that, I will want to go to my topic of today's discussion, is that how satellite observations are helping us to understand the inverse models, which is like a top-down estimation or the Earth system model development. So this is a kind of a summary from the previous COP25, and where SBS in SAPSTA 51 recommended that we should use more systematic observations to improve the Earth system models or the other climate models for further development, and the regional climate models also. And so we basically, I think David Cripps and I were present in this SAPSTA negotiation, or the drafting this document, and we also followed up one analysis to show how we can evaluate the Earth system model, which is also, it was mentioned that we project to the future, and also used a lot in IPCC kind of assessment reports. And we also do the atmospheric inversions using surface observations. And here you're using the GOSAT observations since 2009, or CO2 observations since 2014, and we compare our inverse model, or the Earth system model in this case, and I try to understand what's going on in different parts of the world, because the surface observations we have right now does not cover as much as the satellite observation covers. And by doing this analysis, we can show that the tropical land, the carbon cycle in the tropical land and the climate interactions are not so well reproduced in the Earth system model as well as in our inverse model. So there is scope for improvement, and we can identify by doing this kind of analysis. Then also by this kind of inverse model results are produced using observations, and these observations and then based on estimation of CO2 fluxes And fluxes means that we say that it's removal, but it is negative from the atmosphere, and it's positive is we are emitting. In this case, it's a bit different. But anyway, so what we are showing here is that the inverse model results and the Earth system model results in CMIP 5, IPCC AR 5, and CMIP 6, which is used in IPCC AR 6. And you can compare for the land regions with latitude and ocean regions with latitude. And you can see that the CMIP 6 models are performing better than the CMIP 5 models. So this is helping us a lot to improve our model, understand our model. And now I move into some of the new results we are now producing by using inverse model. The inverse model, I think most people know when we refer to that is a top-down model, and where observations are used and we solve an equation to get the optimized fluxes for different parts of the globe. And by doing that, what we can produce is that we start with a kind of initial fluxes, and then the flux we define again, like I want to say, positive means it's emission to the atmosphere, and negative means it's removal from the atmosphere. And so the land is generally a sink, but then we start in the inverse modeling, we can start with any kind of fluxes. In this case, it's like zero emissions everywhere in the world, on an annual basis everywhere in the world, and we can estimate fluxes, and it comes down to this level, which is like a black line here, the mean. And then we can also start here, which is like the model by Itosan, and then we can also again do inverse modeling, and we can reach to the meeting points. And then this is what the inverse model does. So given the observations, we can produce an optimized solution from any levels you start from. And that's a kind of a priori, and then the bottom up and top down kind of comparison here. And same thing you can do also for ocean, and you can again produce a flat ocean or the uptake or removal increasing ocean, and again you can come up with a mutually optimized fluxes. And you're using now that before you are using like a single model, now you're using ensemble of models so that you can produce a mean value, ensemble mean, and also you can give an uncertainty for each of the estimations we do. And here is a comparison with, not comparison, like I say, 5-year mean fluxes of CO2 for 15 land regions, which is just marked here. Don't need to worry about too much details. But yeah, we can actually give the fluxes for every region and with the mean values and the uncertainties. And also same thing for the ocean region. We are showing for 11 ocean regions, and then the total land and the global ocean regions. And for every region, there are 4 box plots, which is like for 5 years mean, like you plan in the global stock take. And so most of the results we actually understand why the sinks are high in the North America, for example, or why the tropical lands are kind of sourced because of deforestation. But also you understand some of the things like that Southern Ocean sink is increasing because we know the partial pressure in the atmosphere is increasing, so more CO2 goes into the ocean, and those things are happening. And then we can also do that something I don't understand is that the Chinese sink is increasing so fast. And sometimes we think that there's a fossil fuel bias which can affect the CO2 fluxes in derivation by inverse modeling, because it's compensated for the bias in fossil fuel fluxes. So sometimes we see a nice thing for the ocean sink here, for example. I say it's increasing continuously, but for the land sink, it just goes down in from 2001 to 2005 to 2006 to 10, but then it just again remains there. So these things are we understanding details, but nevertheless, the trends with the time, I think, are estimated well in 5 years interval, and it can support global stock take. And so then we have the methane in this case, to sound a little bit. So we discussed about 3 decades of methane emissions estimation by inverse modeling, and because methane emissions were increasing before, and then it was like a stagnant for some times, and again it's increasing. And this gives a challenging thing to understand why this is happening. We find out from the inverse model and the bottom-up estimations that they are for the oil and gas exploration in the 1990s, and then now it's like a more mix of the things, which is like animal farming, coal mining, and then waste management. All these things have increased in the recent decade, and we have increased methane growth rate. And do also again, my point is to show satellite inversions, how satellites help us to derive more information is that when you take a gradient of methane from the SOA to alert in the Alaska, the Canada, and then we can see that there is a mismatch in the a priori fluxes, which means that our model is higher than the observation. But doing inversions, we can actually bring them together, the concentration come together. By doing that, it optimizes the fluxes, it reduces the fluxes in the northern high latitude, 30 degrees, 60 degrees north, and we can actually match the observations. And how can we validate that? Then again, we go to satellite observations to show that there is a northern high latitude bias in the a priori emissions, the bottom-up estimations, and which also gives a negative positive bias in the GOSAT minus models X methane. And by doing inversion again, we can bring a kind of more gray, which is like a near zero bias, which means the satellites are actually helping us a lot to improve our understanding of the greenhouse gas budget and help us to improve our inverse models and the Earth system models, other things. So I think this is my conclusions. I do not know how much I'm doing, how I'm doing in time. Maybe I will not read them. And so these are my conclusions, that we are supporting a lot of activities and contribute to the things. And yes, I think I will just not read all of them right now. With that, I will stop. Thank you.
Thank you, Batra-san. Okay, up next, we have Dr. Dave Clisp. Dr. Clisp is a senior research scientist at NASA's Jet Propulsion Lab and California Institute of Technology in the US. He's an atmospheric physicist serving as a leader of the NASA's Orbiting Carbon Observatory mission, OSIO-2 and OSIO-3. And also, he has a greenhouse gas lead for the Committee on the Earth Observation Satellite or Atmospheric Composition Virtual Constellation. Dave, are you ready for that?
I am. Can you hear me well?
Yep, perfectly. Right, take it away.
Fantastic. You should see my first slide, which is
yes.
I'm honored today to have an opportunity to present to you an international effort to compile estimates of carbon dioxide and methane emissions from space-based platforms. This international effort, as Oda-san just mentioned, is led by the Committee on Earth Observation Satellites, a group of 34 different space agencies that have come together with a number of associates, and then the committee, the coordination group on meteorological satellites. So this is another group of about a dozen different nations that have come together. So as you heard from Ito-san, the countries of the world are now in the process of compiling bottom-up inventories of emissions of carbon dioxide, methane, and other greenhouse gases. And they do this, we call it bottom-up, because they start by counting the number of barrels of oil, or the number of tons of coal, or the number of acres of land that have been transferred from forest to agriculture. And they estimate the amount of emissions of carbon dioxide and methane and other gases that were emitted by each of these processes. And they compile them and add them all up and get country inventories. Another way to do that, is you've just heard in particular from Ito-san and also from Patra-san, is one can make detailed measurements of carbon dioxide and methane in the Earth's atmosphere. We know how much gas was added to the atmosphere. And then we actually put these measurements into a transport model to determine where those emissions of carbon dioxide and methane came from. So the advantage of these top-down budgets of carbon dioxide and methane is that they're very good for tracking emission hotspots. So they're sometimes missed in the bottom-up inventories. And they can also detect changes in emissions by the natural biosphere, the forest, for example, as they evolve and respond to climate change. So our hope is to put these two different kinds of methane methods together. Now, how can we make these measurements? Well, as we heard earlier from Ito-san, we have been making measurements of greenhouse gases in the Earth's atmosphere now since the 1960s from a whole host of different stations. And now we get a few hundred measurements every week from this group of ground-based stations around the world, making very, very precise measurements of carbon dioxide, methane, and other greenhouse gases. But recently, in 2009 in particular, they were joined by the GOSAT mission, making these measurements from space. And more recently, the OCO2 mission, the GOSAT-2 mission, the OCO3 mission on the International Space Station, and the Tropomi instrument on the Sentinel-5P platform out of the Copernicus project in Europe. So we're getting more and more measurements. These systems don't make a few hundred measurements every week or so. They make millions of measurements every month over the entire Earth. And so we can get very, very good coverage of carbon dioxide and methane emissions across the entire world with this emerging and growing fleet of satellites. And when I call it a growing fleet, it's actually growing quite quickly. Right now, we only have a few satellites up that are making measurements of carbon dioxide and methane. But over time, the number of satellites is going to increase substantially, including, for example, the next Japanese satellite, GOSAT-GW, scheduled to launch in 2024. So what are we going to do with all of those measurements? Well, we're going to put them in models very similar to the ones that Patrick-san just described, and we're going to estimate emissions, the total emissions from every country around the world, and then we're going to try to define which fraction of those emissions come from fossil fuels versus which fraction come from the land biosphere, from land use practices such as agriculture and forestry. And so we're going to be able to do that nation by nation. And to prove what we can do, we took the measurements that we have today. They're not perfect, but we did the best we could. And we compiled national scale inventories for all of the countries that were maybe larger than the country of a country the size of, say, Turkey, for example. And we were able to compile emissions from all of those countries and define them in terms of fossil fuels, for example, shown here for China. In the USA, we can calculate the fossil fuel emissions. We can also calculate the amount of uptake of carbon dioxide by the land biosphere. And we've done this for a large number of nations around the world. And we've delivered these inventories to the UNFCCC. We've done this for methane as well. And the story there is very similar. We were able, with the current measurements from the GOSAT satellite, to make measurements from emissions from about 58 countries. And we've divided those into emissions from agriculture and waste, fossil fuels, and natural sources such as wetlands. The 5 main emitting countries in the world, China, India, Brazil, the US, and Russia, are responsible for about half of all of the methane emissions from man-made activities. And we're tracking those. For most of those countries, most of those emissions come from the agricultural sector. From Russia, though, most of them come from the fossil fuel sector. So as we go forward in time, we'll be able to make increasingly precise measurements of all of these areas. So we can also make measurements, as you've just heard from Stosan, of individual cities or even individual power plants using these space-based measurements. And these can help to compile the bottom-up inventories that are being produced by the national inventory communities. Here we're showing the GOSAT emissions measurements that we use to actually track the effects of the lockdowns associated with the COVID-19 pandemic. And so what we were able to do there was to track month by month and year by year the emissions of carbon dioxide from a host of different cities, Tokyo shown here. In addition, satellites like OCO2 can measure the emissions from individual power plants. This is OCO2 flying about 100 kilometers away from a large power plant in South Africa. We were able to track the emissions from that power plant and estimate the emissions to within about 10% of what was being measured by the in situ in that power plant. The Tropomi mission out of Europe is now making similar measurements of methane. This is over West Texas, and these are fossil fuel extraction activities that are leaking methane by accident into the atmosphere. And we're now able to track those and tell the companies that they're losing methane and losing profits into the air. They're actually quite thankful. We don't have the capabilities today to measure every point source on the planet, but as time goes on, we'll be getting more and more satellites flying that can make these measurements. The main objective of these activities, though, is actually to start a conversation. As I mentioned, we have two different groups compiling inventories of fossil fuel emissions around the world. We have the national inventory communities that are compiling the inventories that are turned into UNFCCC for the global stock take. And what they do is make measurements in all of these different sectors and then add them all up to come up with a national inventory. In a completely complementary fashion to that, what we do is we make measurements of the emissions around the entire world with great accuracy and now greater and greater precision, or greater and greater resolution, I should say, and we compile those into national inventories of emissions, and then we try to attribute those emissions to individual countries, individual sectors in those countries. What we're hoping is that by combining these bottom-up inventories with these top-down greenhouse gas budgets, we can actually produce a more complete and more transparent global stock take around the world. These kinds of top-down methods will be getting better and better as time goes on. And here we're just providing some pilot products that can be used to start this conversation in a very serious fashion with the parties involved. If you'd like more information about these pilot top-down products and what we're able to do today, please go to this website, which is https://global-stocktake, greenhouse, and in particular, we have measurements there showing these particular inventories for carbon dioxide and methane that I just introduced very quickly. We also have inventories of above-ground biomass, agriculture, forestry, land cover, and mangroves as we track how the natural biosphere is adapting to the climate change. So with that, thank you very much for your attention, and we look forward to your questions.
Right, fantastic. Thank you, Dave. So the last speaker before the panel discussion is Dr. Masataka Watanabe. Dr. Watanabe is a professor at the Research and Development Initiative at Chuo University. So he has been working on biogeochemical modeling with a focus on the interaction among atmosphere, land, and ocean. And he's been working in the Asian area. He'll be showing some examples of how we can use the science data for helping the inventory compilation. Watanabe-san?
Okay, can you hear me?
Yes, perfect, loud and clear.
Okay. Thank you very much, Mr. Oda-san. I'm pleased to contribute to this seminar from the lesson learned at the research on satellite-based estimation of GHG emission sink in Mongolia. Over 50% of countries did not submit the biennial update report, BUR, to the UNFCCC yet, which is the essential documents to achieve the targeted goal of GHG emission reduction in the future. There are two major gaps which are responsible to this situation. Number one, knowledge gap. There has a difference between actual and reported emission sink, the so-called missing source and sink, due to the data quality of national statistical and limitation of the emission factor of the IPCC guideline. Number two, resources gap. BUR is hard for many countries, non-Annex 1 party in particular, due to human resource limitation, internally long process for completing reports, and shortage of budget. Satellite-based estimation of GHG emission sink can fill this knowledge gap of missing source and sink for supporting accurate GHG inventory. Reliable regional atmospheric transport models, such as WRF-Chem and many similar models, are now available and has been used by many researchers in the world. Vital needs exist in satellite-based estimation of GHG emission sink on national, regional scale using a reliable regional atmospheric transport model available to everyone, with inversion analysis to fill these two gaps. Mongolia's main energy source is coal, produced in its own country. In Ulaanbaatar, the capital city where about half of Mongolia's total population lives, CO2 emitted from coal-fired power plants, heating boilers, and gasoline accounts for about 75% of the national emission. Located in the valley, UB City is surrounded by sunny weather and beautiful grasslands in the summer. But when the winter temperature reaches -30 to -40 degrees Celsius, a strong inversion layer is formed and the world's most serious air pollution appears. Based on the Japan-Mongolia policy dialogue, a joint research team between the two countries developed an air pollution and CO2 concentration prediction model for the whole of Mongolia and UB City. The model is based on WRF-Chem and calculated using the boundary values obtained from TM3 and NCEP reanalysis data. Behaviors such as smoke from the chimneys of coal-fired power plants in UB City, smoke emitted from households in the Gale area, and exhaust from automobiles were calculated. Due to severe air pollution in winter, the monthly average PM2.5 concentration continued to exceed 200 micrograms per cubic meter. And in winter, when CO2 emissions were the highest, GOSA data could not be obtained at all, which made analysis difficult in Mongolia. However, due to the use of briquette fuel in the Gale area, which was introduced as an air pollution improvement measure in 2019, the PM2.5 concentration was reduced to about half, and the acquisition rate of GOSAT satellite observation data were dramatically improved, but no reduction in CO2 emissions were observed. The total CO2 emissions of Mongolia are overwhelmingly smaller than the CO2 flux that flows across the upper troposphere. So it is essential to analyze the emissions from the surface only and flux that flows through the upper troposphere separately. Therefore, for the emission from the ground, partial column GHGs, JAXA EORC data was used. We developed jointly the model that can estimate CO2 emission sink in Mongolia by inverse analysis using GOSAT series observation results and the green function using WRF-Chem VPRM models. Key message and its contribution to global stocktake. Number one, the annual total CO2 emissions in 2018 estimated by the inverse analysis were revised by plus 1.1% compared to the Mongolian national CO2 emission inventory in 2018 based on GDP estimates. When the standard errors of CO2 GOSAT observation and CO2 emissions were 2 ppmv and 400 tons per hour, respectively, and a maximum error was 5.3% in sigma base. Number two, estimated sink by grassland in 2017-2018 had compared with on-site measurement data, and excellent agreement was obtained. Error average between observed and simulated values of 0.08 micromole per square meter per second. We need to continue efforts for the evaluation of land use change, and forest and methane emissions. Number three, The next Mongolia's BUR would utilize and include these developed emission results as reference information. Number 4, the methods for estimating GHG inventories co-developed with Mongolia is ideal for establishing a sustainable approach when Mongolia uses it. And finally, we have planned to apply the above GHG emission sink estimation model using GOSA satellite data to other countries, such as Central Asia, under the cooperation of the UNFCCC. Thank you very much.
Right. Thank you, Watanabe-san. Also, thank you to all the speakers today. Now we will move on to the next part of this event, which is the panel discussion. So, are there any questions online? So before collecting the question from online, let's start with the live audience. Then if you have a question, let us know. When you're asking a question, please introduce yourself and also be clear who the question is directed to. And also, in addition to 5 speakers today, now Ms. Moiko Yoshitomi from Ministry of Environment Japan, also Dr. Nobuko Saigusa from NIS is also joining. Right. Yes, please. Would you mind coming up to podium?
So, Stephen Hamburg. Stephen Hamburg from the Environmental Defense Fund. Really exciting talks, and I think the potential to better resolve emissions is really critical and exciting. But I'm not sure this is a question just for David Crisp, though he raised it. We need soon the ability to resolve the data into much finer spatial scale and be able to do this in a near real time. How realistic do you see with the data from both JAXA and elsewhere to be able to do that? Because that's what we need to be able to take the mitigation action that the world needs.
Thank you for that question, Stephen. I anticipated it. What we're trying to do with the national activities, the public sector missions, is to map out the entire world with tremendous precision. So that we can actually detect a range of sources that even include not just discrete point sources like methane emissions from pipelines or from cities, for example, but also to pick up methane emissions even from things like natural wetlands. But these are now being complemented by methods that are coming from the commercial sector, where they really a large series of commercial satellites with very, very high spatial resolution methane imagers are coming online. They're not quite as sensitive to the kind of low-level emissions that are produced by the natural systems, by things like agriculture, but they are sensitive to very large emissions from what we call super emitters that are really responsible for a very large fraction of all methane emissions. So for methane, we'll see a combination of the public sector and the private sector working together to look at different parts of the system. Now, the other thing is that at the moment, the space-based measurements only constrain 2 greenhouse gases very well, and that's carbon dioxide and methane. And the high-resolution methods only constrain methane at this point. They can constrain CO2, but only enormous emissions for CO2. So once again, we'll all have to work together with our colleagues in the ground-based community because the ground-based community measures all of the greenhouse gases that are important for the stocktake. So once again, working with the commercial sector, the public sector, the space-based community, and the ground-based community, and working together as a team, we can actually start to answer these questions. And I have a great deal of faith that even though we're not quite there today, as we move through this decade, we will be learning more and more how to do this. I hope that answers your question.
Right. Yeah. Thank you, Dave. Any other question online or for live audience?
Oda-san, may I introduce one question and
Yes, please.
answer from the online? One question from Oksana. There is already partly responded from Patola-san, but there are many groups that produce observations-based emission estimates via inventories. And then her question is there an international standard that the groups can use to ensure consistency of these estimates? This is a question, and there is one answer here. Perhaps one is from Niwa-san, and Global Carbon Project use the same common fossil fuel emission data. That is one way to ensure the consistency. But is there any response? Perhaps may I ask Patra-san or other Ito-san or David Cripps-san? Anyone, if you can answer.
I guess David is better for this because you are doing the CEO's thing, you said, and but I think, yeah.
Well, once again, what we're doing today really amounts to a series of different science experiments to see how to best do this, answer these questions, and meet these requirements. As time goes on, we will need organizations like the World Meteorological Organization's Integrated Carbon Dioxide Information System to act as clearinghouses to help us define a series of very specific requirements. And then also we'll need assessment organizations like the IPCC to step in and actually help us out to find out how do we bring all of these different kinds of information together. The bottom-up information, the top-down information, the satellite information, the ground-based information. All of these have to be put together. Also, many different organizations, Patra-san's organization, also organizations like the European Center for Medium-Range Weather Forecasting and others are putting together individual inventories based on all of this information. And so we'll have many answers there as well. But by actually doing the best job we can within the international community, both the policy community and the science community, we think we can bring all of these together, just as we have, for example, your daily weather report. That also comes in from many different sources. There were many different data sources, many different models that come with that, but we have international organizations that have come online to help put those together and get them out to the community while they're still very relevant. We'll need to do that for carbon dioxide and methane and other greenhouse gases. And by putting things like the pilot inventories that I described and Patra-san talked about on the table, today, we can start that conversation, start that process. I hope that answers the question.
Thank you very much.
Thank you, Dave. Yes, would you mind coming to the podium? Yeah. So here's one more question from the live audience.
Thank you very much. Very excellent sessions. And so I'm very interested about the GHGs, the emission from ecosystems, especially the tropical. Because of this GOSAT data showing the high methane emission, maybe that is related to what is a wetland and the peatland. So why in this ecosystem high the methane emission, maybe that is related to redox potentials in ecosystems. And so normally very difficult to directly evaluation the redox potential ecosystem using satellite. And so we evaluate the two factors. So one is water condition, and the second one is nutrient conditions. So high water tables and high nutrient apply, Then so the reduction potentials drastically decreasing. Then so the methane emissions, which mean this ecosystem related to water tables and the nutrient supply, especially the sediment or something, the clay, the supply from the river, flooding rivers. Then so I'm very interested about the GOSAT data. And so this situation changing by the seasonally. And so, but you know, normally the tropical zone covered by the cloud, so difficult to get this kind of data. But I'm surprising that you provided very excellent sequentially data. So how to evaluate, or this is the apply to evaluation of this reduction potentials. So this is my question.
Thank you very much. This question is very important for tropical carbon budget, including the Southeast Asia, with a very wide, extensive peatland. And in our project, we have both bottom-up and top-down components. And in the bottom-up components, we have ground-based measurement data, the flux measurement tower in Southeast Asia. And also, we have a biogeochemical model, including the methane production and emission pathways. So in this model, the impact of groundwater table depth or inundation expansion or reduction is included. So by using this kind of data and models, we can estimate the methane emission from tropical wetland and peatland. And also, as you pointed out, the GOSAT is very important, but sometimes this satellite cannot provide useful data for tropics because of cloud contamination. So we can estimate the tropical wetland emission of methane using both bottom-up and top-down approach, using some combined or integrated manner. Thank you. Okay.
Right, thank you, Ito-san. Also the question from the audience. So I see a couple more questions online, but we probably want to move on to the panel discussion. But you're still welcome to submit a question by online, and actually our team can answer the question online when possible. So feel free to do so. Also, we try to address some of the questions from audience too. So okay, so now actually move on to the panel discussion. We prepared two questions. Okay, so can you show the first question? So this is a question directed to speakers for today. I'm going to ask, how can we utilize the knowledge and information you provided from your research to support your current emission reporting and assess our climate mitigation progress towards Global Stocktake 2023? Who's going to go first? I see Patra-san on my display.
Okay. Yeah, so I think this is one thing we must do and we have to do. And I was trying to show in my presentation is that, I mean, I am an inverse modeler, so I will provide information from the inverse modeling. And I think there should be a multiple line of assessment or estimation has to come to the same table. And then we evaluate each of them. Or even the inverse model itself will be like there should be criteria, like what David also mentioned that yeah. So we do actually a lot of evaluation because we, if we do a modeling methane and CO2, we have to evaluate our transport in the model. If you are doing methane inversions, you have to evaluate transport and chemistry in the model. So all these steps are done before actually we do the inversions. So every model has their own characteristics. And and based on the evaluations, we have some knowledge about which model does what. And one thing we have also learned in the Transcom experiment and the GCP experiment is that we cannot estimate with very high confidence the net sources of sink given the point, but for a given region, we can estimate very well how the emissions are changing with time. The trend, for example, if you have a baseline, what you are supposed to do in the global stock taking, that if you define a baseline and you estimate a trend, how it is changing for a country or for a region with time, that actually the inverse model does pretty good. So, and if you put like multiple inverse models and try to see the anomaly or the trend from a baseline, and they all agree very well. And as I said also, okay, whatever prior fluxes I can start with, my inverse model can produce a trend or the variability very well, because the model has a one quality that the transport has a maybe even a bias for a region, but that it is consistent over the years and years. So the emissions we estimate are actually very solid in terms of the trends in emissions, trends in removals. So I think that's what I would say, that we are in a good position in some sense for the inverse modeling point of view to track the changes in emissions every 5 years interval.
Yeah, thank you, Bajiro-san. Anyone want to follow? How about Sito-san?
Okay, so I think the observation is only the tool to visualize the mitigation effort, mitigation progress. So at first, we have to understand our situation correctly. So as I presented in my presentation, our JAXA, we newly released a new product. So 10 years ago, the space-based greenhouse gas observation is very challenging, but now it's just a powerful tool to estimating the global, to measuring the global CO2 and methane precisely. In the next step, we have to identify the further enhanced emitter area or sector to retrieve this area or sector. We believe our latest, our new product is very powerful because our product, including the reflecting the human activity directly. So, in addition, our decade-long GOSAT data has a lot of information, both emission and sinks. Then we hope our new product and also the long decade GOSAT data will contribute to mirror our mitigation effort in the observation results.
Thank you, Sito-san. So Watanabe-san, you're using the JAXA new product. So could you share your thoughts on this?
Well, thank you, Oda-san. In my presentation, I already discussed about the knowledge gap and resources gap. And in terms of knowledge gap, I emphasize on the missing source and missing sink problem. In particular, in the Mongolia case, Mongolia is a very arid or semi-arid climate, and therefore the ecosystem is very sensitive to the availability of water. So from year to year, the sink is highly depending on how much water is available to the ecosystem. And so I think it's very difficult to evaluate only by the inventory bottom-up type the approach to evaluate this sink in this semi-arid or arid condition. In that case, we really have to have a real-time changing satellite data observation to monitor not only the CO2 flux, but also the mechanism behind this flux, particularly in the water availability by satellite. So I think our approach of filling the gap in the scientific gap is very useful, I believe. And also, in terms of the resources gap, as I say that over 50% of the countries are not submitting BUR. And this situation has to be also improved in order to accelerate the activity of global stocktake, because the BUR is the basic document to evaluate the future CO2 reduction or current condition of the CO2 emission, and also future scenario for the CO2 reduction. Therefore, one other aspect is how we can help to encourage those countries who did not submit the BUR or BTR soon. And I think some kind of the unified approach, like top-down, but still my approach is bringing the regional aspect, not the global, completely global model, but rather regional aspect is also important, because each country do not believe whatever the global model said, because they do not feel what is the truth to their country. So I think from locality point of view, I think the contribution and working with these countries is also very important. I think that's my understanding about how to contribute to the global stocktake, scientific gap and also resource gap. I think these gaps should be resolved by the approach which we discussed now. Thank you.
Yeah, thank you. So Ito-san, you want to follow up?
Yes, today I show the result, a very brief overview of our S28 project. One advantage of our project in terms of global stocktake is the coverage of Asian Pacific region. So in contrast to Europe and North America, this Asia Pacific region lacks integrated or comprehensive framework of greenhouse gas observation, because Europe has some Copernicus program, and North America has the North American Carbon Program. But in Asia and Oceania region, we don't have such kind of programs. So, but our S28 project can provide various kind of observational data in this region by ground-based aircraft, ship, and satellite data. So we can provide estimation in this region to fulfill the gap of the regional greenhouse gas budget. But there remains one more very serious kind of gap. This is international coordination. Our S28 project is mainly by Japanese researchers, but we don't have intimate collaboration with Chinese or Korean or Southeast Asian people. So such kind of international coordination is the next step to accomplish the very more and more ambitious program in this Asian Pacific regions. This is very important task for the researchers to make more contribution to global stocktake. Thank you.
Thank you, Ito-san, for your perspective. Sorry, Dave, I made you wait. You're smiling, so yeah, floor is yours.
That is fine. I would like to also echo that the main thing that we can do as a scientific community to contribute to the global stocktake perhaps is not really so much just providing information, but providing information with great transparency. And to do that, we don't just need better measurements. Of course, we need better measurements. We need better accuracy, precision, resolution, and coverage with our measurements. We don't just need better models, but of course we do need better models to retrieve estimates of carbon dioxide and methane from our space-based measurements, and also models to actually assess where the fluxes are coming from given those measurements. More important, though, we need better communication and coordination and collaboration among all of these different groups. We need to be able, in order to actually do that, though, we probably need to actually start thinking in the terms of capacity building. We need to make sure that the communities that could use the measurements that we're making can actually understand what are the best products and what are the best practices for putting these different systems together to actually start answering questions about the global stock takes. So once again, even though we do need better measurements and better models, we need better collaboration and better communication to actually make these systems truly transparent and useful to the global stock take. I hope that helps.
Yeah, thank you, bro. Actually, you're left out. First question. Okay, so let's move on to the next question, which is, I'm going to leave this. Where to go? You already seen this. Yes. So the second question is the kind of follow up the first one. What changes in society would you like to see, and or think need to happen, or should we see, and do you detect them? How do you detect them, and or how do we make those changes happen? So this is actually, so we want to hear first from the Yoshitomi-san and also Saigusa-san for this question. So maybe Yoshitomi-san, do you want to go first?
Yes. We can only manage what we can measure. We are encouraged to take more proactive climate action and come up with more ambitious targets if we see significant changes in emissions before and after action. We are supposed to get more conscious about air quality. Yes, we recognize the importance of Earth observation as an information source for climate action, as well as a vehicle for solutions supporting decision-making on climate change, adaptation, mitigation, and mobilizing finance. Therefore, we would like to contribute to constructing the global system, combining atmospheric GHG concentration measurements with human activity data in a modeling and analysis framework to help decision makers all over the world take better informed action to reduce emissions of GHGs and pollutants that reduce air quality.
Great, thank you. How about Saigusa-san? Can we have your thoughts on this?
Okay, so the question is more bigger and bigger. So, and what I'm thinking is that a number of people have already mentioned, but one thing is making greenhouse gas, global greenhouse gas cycle more visible with high temporal and spatial resolution, and not only greenhouse gas budget, but also I'd like to see more visible data set on future climate change or future air quality, as Yoshitomi-san mentioned, or future food production potential. And those, such kind of integrated data set and integrated knowledge, we can somehow think about our Earth more sustainable. So as a scientist, I'd like to work for that. Thank you very much.
Great. Thank you. Anyone want to follow up? Who's hiding? Don't be shy. Shito-san. Oh, so sorry. The person you said something. Go ahead. Please go ahead.
We cannot hear you well. I cannot hear you well, basically.
Oh, you couldn't hear well.
Okay, so maybe I should say.
Yeah, we can hear.
So yeah, I do not know that what changes. A lot of changes in society you need, but I think all comes to consumption, how to limit consumptions, right? So we emit CO2 by consumption, we emit by methane by consumption.
Right.
So it can be like a lot of things in the agriculture for methane and CO2 in the industry. So I think everything comes down to how much can we change in terms of consumption habits, like whether you get energy from the renewables or you get energy from the coals. So there's a lot of discussion happening right now, at COP. So and also same thing whether you eat more beef or you eat more vegetables. And all this, so I think that this it will come down to those kind of things eventually, and it will be difficult to change any culture so quickly. And to detect, I think the system will detect eventually, because at least from my perspective, the global models we do, and we have a budget there, so we cannot miss the budget, because atmosphere keeps the record of the global total emissions. The global total emission nobody can deny, or because regional emissions you can always bargain that my emissions are less, other emissions are more. But globally, the emissions are all counted for methane and CO2 or N2O. So this is why I think we should be able to detect them. I mean, if somebody like it's a one place maybe you can miss, but eventually we catch all the emissions in global scale.
Right.
I think so. The detection will not be a problem when you are making an effort to reduce, let's say, 10%, 20%, 30% emissions.
Right.
I think that's all I say.
Yeah, great. Thank you, Patra-san. So let me add a little bit of context on this question. So for example, if you're talking about electric vehicle, for example, we are trying to reduce CO2 emission, and probably you might see something different signals in the atmosphere, and we probably need some new instrument. Then I guess maybe Shido-san, you want to say something about this?
Can you hear me?
Yes.
Okay. So, as people mentioned already, so I believe the visualization of the greenhouse gases emission map or distribution are very important, and also to understand our mitigation efforts is also important. To visualizing this signal, the monitoring or observation is only the tool. So especially the remote sensing observation from the space, satellite base, or including the airborne base, can provide not only the concentration information, but also the spatial distribution information. For the person, it might be helpful to understand our situation with visually, and also we have to inform the emission changes to track the emission changes to understanding our situation. So I believe we have to continue the greenhouse gas observation from space as long as possible, and monitor the mitigation progress by the satellite observation. Hopefully, I'd like to continue the GOSAT observation as long as possible, and contributing to the public to understanding our mitigation progress by the GOSAT data.
Great, thank you, Shido-san. How about Dave? So as we move forward, what kind of data we need? I think this is the kind of relevant topic based on the earlier questions. You want to add something more?
Well, just a tiny bit. Going back to the beginning of this question, We can only manage what we can measure. And so over the next few years, hopefully we're going to see a large number of nations and even individual subnational entities like cities start to try to find ways to mitigate their emissions, to reduce their emissions of greenhouse gases. And one of the first questions that they will be asking and that their constituents will be asking is, how well is it working? Are the methods that we're actually putting in place actually working better than the methods that the next city over is putting in place? As the measurement and modeling community, we can help in that way, I think, in really the best possible way. But to make that work, we have to work very closely together with those entities, with those nations, with those cities, to help them understand what they're actually what they're emitting and how that's changing over time and how effective the methods that they're putting in place are working. We can also help to identify things that are what I call low-hanging fruit. They are places where a small change in society can produce a big reduction in greenhouse gases. And so where those things exist, we'll be able to see them everywhere in the world, and we'll hopefully be able to work with the entities, with the groups that are responsible to help them to actually make the change. And then as they go forward, we'll help them to monitor their progress toward those changes. So we're hoping that this collaboration between the scientific community and the public policy community can help to actually implement these changes that we're all hoping to see happen with increasing regularity as we go forward into the future. I hope that helps.
Yep. Thanks, Dave. So now, Watanabe-san, you have a specific example of how we can use the satellite data for helping producing inventory information. So can we have your thoughts on this question?
Thank you, Oda-san, for your question. I feel that as David said, that you're right, that without measuring, you can't control anything. But same thing I can say in other way, that without knowing the how much of the reduction can be effective to certain the devolution or improvement of your society. My question is that maybe any kind of the effort by the human being, even I'm talking about the case of Mongolia, which is a rather small emission of GHG, and any kind of change or improvement of the emission in Mongolia, for example, can we detect by the satellite? I think that's the basic question I'm always asking to me. And people are not enthusiastic to do their own effort unless they can see what kind of change they have done by some kind of sensitive method of the measurement. So if we can increase the sensitivity, measurement sensitivity of satellite, and watch any kind of change in Mongolia, I think winter time, I think it's no problem. They can detect how much of reduction. For example, I show that briquette fuel introduction may introduce lots of improvement in air pollution, but not CO2 emission at all. So I think my question is that maybe in order to link the measurement with the change of behavior, I think we need a kind of a much higher sensitivity in the measurement system, particularly in the satellite measurement. If we really would like to utilize this system into the innovative the drivers to change the human society's behavior. That's my impression. By doing the exercise in very clean, the summer time is very clean in Mongolia, very dirty in the winter time in Ulaanbaatar. I think I think that kind of a system is necessary. That's my impression. Thank you.
Thank you so much. So it's almost time. You're so quick. So the Ito-san wanted quick something? Yeah. Right. So the last of all, from last speaker, Ito-san, quickly add the perspective.
Yeah, only one thing I want to add. In terms of society, more than half of emission occurs in urban area, in so-called city. So we need to monitor the greenhouse gas emission from city or urban area using a very high resolution observational data and emission inventories. That's the key technology for the contribution to the human society in the future, I think.
Thank you, Ito-san. Okay, so we are almost done. So now we're trying to, we want to conclude this event. Thank you for your participation for today. We hope you enjoyed this science talk, also discussion. I also we would like to thank the sponsors for allowing us to partake this event. And also we'd like to acknowledge the team members who you cannot really see, but who made this event possible. And yeah, so with that, we will end this session. We hope you a great COP weeks, and also virtually or here in Glasgow. And I hope to see you on the next occasion with lots of progress on climate action. So bye for now.